Hey everyone, in this lecture we're going to be talking about groundwater. We've already talked about other different processes of the earth in terms of oceans, as well as when we have too much water from rain and things like that, what happens to landslides when we have mass movement. Now let's talk a little bit about groundwater. So some of the things we're going to cover in today's topic is, well, what's groundwater? Where does it come from and how does it flow? The nature of the water table and factors that determine its depth, how wells and springs provide access to groundwater, and how groundwater supplies can be damaged or depleted. So first, let's define groundwater. Groundwater is the liquid water that resides in sediment or rock under the surface of the earth. And this accounts for about 2/3 of the Earth's fresh water resources. And we use fresh water for our drinking water, for cleaning our clothes. We also use it for agriculture, for watering our crops. And there's other industries, of course, that use fresh water. And when I say fresh water, a majority of that is underground. So what are these underground reservoirs and how does water get there? We have two different ways, and majority of that is from connate water. And this is water that's buried with sediment grains during deposition and gets trapped when the rock liquefies. And the other is meteoric water. And this is where water is precipitated from the sky, such as rain or snow, and it falls on the land. If it does not evaporate directly back into the atmosphere, or if it's not trapped in a glacier, the water sinks or percolates downward into the ground through infiltration. And this is where the uppermost part of the crust acts like a sponge and it can soak up all of that water. And to do recharge through meteoric water can take a very long time. And so some of the things that we talk about when we say, how does it get trapped within a rock? Well, it has to do with the porosity. And this is defined by the letter sigma. And porosity is the total amount of open space within a material. And when we talked about sedimentary rocks and we talk about their grain size or their grain distribution, we talk about how rounded they are, how they would fit together. And so when we put a jar of rocks in, or a pile of rocks into a jar, we can see that there's spaces between these grains. And when we talked about sedimentary rocks, we talked about the grain size and sorting. All of that has to do with the space between the grains now, and that's called porosity. So porosity is represented as a percentage, and there's two different types of porosity. First is primary, and that's the open space that remains in a sediment after deposition, and it exists because the grains don't fit perfectly together. And then the other is a secondary porosity, and this is where new pore space produced from a rock after it is formed due to like fracturing, or if there's faulting or something going on, where it creates a porosity, secondary porosity, other than the space between the grains. And then the other thing that is important to groundwater and groundwater flow is permeability. These are the two main principles here that we need to think about. And permeability is the ability for a fluid to pass through an interconnected network of pores. In a rock, this is how easily fluids like water can be transported through the material. Permeability is controlled by some factors like the number of conduits, the size of the conduit, and the straightness of the conduit. So if you think about running through a maze, like a hedge maze or something, it's around Halloween time, you might think about how quickly it takes for you to run through the maze. If there's all these twists and turns or dead ends, it would take you a lot longer to get from the start of the maze to the end of the maze. And that has to do with the number of conduits. So think about that maze again and how many different paths you could take. And if you think about the size of the conduit, it would be the walls or how narrow the path is. So if it's very narrow and you have to really squeeze through there, that will take longer. It might be harder for you to get through the maze if it's very narrow versus it being very wide. And like I said, the straightness of the conduit, which would be if you have any of those dead ends or right turns or something, that would make it harder for you to go through the maze. So those are some of the ideas related to permeability. So here's a video on the differences between porosity and permeability, and here are some of the questions that we're going to address after you watch this video.
Groundwater represents about a quarter of the US freshwater supply. Most of it's used for domestic purposes or for agriculture. And there are two essential properties of groundwater that we really need to investigate to understand how it works. And those are porosity and permeability.
Today we're going to describe what we mean when we use the term groundwater, and we're also going to examine those two properties, porosity and permeability, and how they affect how much groundwater is there and how easy it is to get it out of the ground.
All the water on Earth is linked together by the hydrologic cycle. In brief, this cycle begins when water evaporates from the oceans. Water vapor rises into the atmosphere and condenses to form clouds. Clouds lose their moisture through precipitation.
Rain falling on land can run off into streams and lakes or may infiltrate through the soil and into the rocks or sediments below. This is groundwater. We want to examine the properties of earth materials that allow this water to be present underground.
When people think of groundwater, they often imagine water flowing through a cave system or maybe an underground lake. While groundwater does exist in these forms, it's not that common.
Most usable groundwater is actually stored in the tiny spaces between grains of sand and gravel. Porosity and permeability control the distribution of this water. We will consider each of these separately, starting with porosity.
We filled this beaker with about 300 milliliters of relatively unsorted gravel. Notice that there are grains of different sizes that loosely fill the container, leaving several visible open spaces. These spaces represent the porosity of the sediment. Porosity is the proportion of the volume of an earth material that is composed of void spaces.
We can do a brief experiment to determine the proportion of space in the gravel occupied by porosity. We have 200 milliliters of water in this smaller beaker. We dyed the water blue with food coloring to make it easier to see. When we pour the water into the beaker, it fills up the empty pore spaces from below, and the water eventually rises to the top of the gravel.
Now, let's look to see how much water we used. Remember that we started with 200 milliliters, and now we have about 80 milliliters left. So we added 120 milliliters of water to a beaker containing what appeared to be approximately 300 milliliters of gravel. That tells us that about 40% of the gravel mixture was composed of air spaces that we subsequently filled with water.
We can try the same experiment with smaller, better sorted sand grains. In this case, it is more difficult to make out spaces between the smaller individual sand particles. What proportion of the sand do you think is composed of empty spaces?
This time the sand mixture accommodates 100 milliliters of water, indicating that the estimated porosity of sand is about 33%, a little less than that of the gravel. In both cases, the water lies in the spaces between the grains.
There are a few big visible spaces in the gravels and lots of small, less visible spaces in the sand. Depending on how well these materials are sorted, they can have similar porosities. The porosity values are not unreasonable for unconsolidated gravels and sands near Earth's surface.
About 80% of shallow groundwater systems in the US are composed of these materials, sand and gravel. In most cases, we can extract the groundwater using wells, in much the same way that we would extract water from the gravel mixture using a straw.
However, before we make this seem too simple, we have to consider the role that permeability plays in controlling how groundwater moves through rocks and sediment.
Permeability represents the capacity of water to flow through earth materials. It's not sufficient that groundwater is present, it must also be able to flow into our well so that we can extract it.
Many rocks have pretty good porosity, but their permeability values will differ. For example, some igneous rocks contain preserved gas bubbles that are not connected. These rocks would have good porosity, but low permeability.
We've designed an experiment to demonstrate how permeability varies among gravel, sand, and clay, the common sediments at or near Earth's surface. We've taken a funnel and filled it with each type of sediment. We added a tiny piece of filter paper to prevent the sediment flowing through the funnel.
Then we poured a constant amount of water into each setup and watched to see how long it took to collect in the beaker below. The faster the flow of the water, the higher the permeability. Let's see what happened. As you can see, water quickly passes through the gravel and almost all of the original water collects in the beaker below.
In contrast, water pools on top of the clay and is unable to flow downward between the tiny clay particles, making it essentially impermeable at the scale of this experiment.
Finally, water passes through the sand more slowly than the gravel, and only about 75% of the original water makes it to the beaker during the time of the demonstration.
The permeability of these three materials decreases as we move from the gravel on the left to the clay on the right.
Sand and gravel make for excellent groundwater sources because of their combination of good porosity and permeability. Other materials such as sandstone, some limestones, or fractured igneous rocks may also have high porosity and permeability values and serve as good groundwater reservoirs under specific circumstances.
Material like clay or fine-grained sedimentary rocks like shale, or unfractured metamorphic or igneous rocks such as granite, have such low permeability values that they often act as barriers to groundwater flow.
We had 3 learning objectives for today's lesson. How confident are you that you can complete these tasks?
So what that video showed was an experiment between porosity and permeability with different soil types. So what did you observe from the different soil types that they used? Well, you should have seen that the water flowed much more quickly through gravel than it did through clay, and that has to do with the size of the grains and the amount of space that's between that grains. So we would expect higher porosity and higher permeability in a gravel than we would with a clay. Are porosity and permeability the same thing? Well, I just explained that they aren't. Remember that porosity has to do with the space between the grains, and permeability is the flow. So in that example, they talked about sand and gravel and clays, but what about a rock that would have low porosity but high permeability? What do you think that could be? Well, when we think about low porosity rocks, we think about things that are very tightly pushed together. And remember that high permeability means that it has high flow, so that there's more direct pathways of water movement or fluid movement. So something that would have a lot of permeability but not so much porosity would be a rock that has a lot of natural fractures or a lot of natural joints that in the rock itself may not have a lot of flow between the grains, but between different components of the rock that would have fractures or joints. So it's a little bit of a trick question, but that's something to get you thinking about what types of rocks have different porosity and permeabilities. So now I'm going to try and draw the difference between porosity and permeability and walk you through it in a little bit more detail. So again, I apologize for my drawing attempt. It's very difficult to do on a computer with a mouse, but here we are just doing the best we can. Okay, so like I said, there's a difference between porosity and permeability. And when we talk about porosity, we have a bunch of grains, and I'm going to color these a different color because I don't want to confuse you. And what shape fill color? Let's color them yellow so they look like grains of sand. Okay, so I'm going to represent all these little circles here, represent individual grains of sand. And these grains of sand are going to be very well-rounded, and they're going to be well sorted because they are also around the same size. Actually, they're exactly the same size because I copied and pasted. Now, if we were to put this into a beaker, or if we were to look at a sample size of this, I'm going to put this inside a box, for example. And so now what this represents is all of the blue space represents the porosity. This is all of that space between the grains. And if these grains were to be a little bit tighter together, they're actually stacked next to each other, or they're very they're being pushed down and squeezed together here. You might actually see how closely these grains can get, and therefore the porosity would change. Now imagine if we had smaller grains. I'm going to add some small grains here, and you can see how, this would have to be quite small. So now you can see how smaller grains take up all these other little voids. And if we get even smaller here, let's show a few more smaller grains. And now what used to have void space between all of these grains is now being taken up by even smaller and smaller and smaller grains. So now we're very well rounded, but we're more poorly sorted, because now we have grains of different size that are taking up all of the pore space in here. So again, if you imagine that the blue space represents the porosity. Now let's think about what that means for permeability. Again, I'm going to copy some of these things over here, and we're going to look at what that means for permeability. Okay, so I'm going to move these around just a little bit first. Again, if we were to put this into a container or a box, permeability represents the flow, the ability to flow between grains. So if I were to represent flow from left to right, flow would be able to very easily go between these grains, just like so. Not a lot of obstruction, okay? So now I'm going to erase my arrows. And let's rearrange the grains a little bit. So now we have all these grains are tightly pushed together. And now they're tightly pushed together. And now you can see that the flow is going to be a little bit more difficult to go between. It's not a straight across like it was before. So now if we have flow, it's going to be obstructed. It's going to barely be able to squeeze between these grains. There's very little space. So now this has much lower permeability here than we did before. So as the image is represented here, this is low permeability. And that's because these grains are being crammed together. It doesn't have an easy path to flow. Now, how I've drawn this is now you can see that actually flow might be a little bit easier in one direction than the other. So for the flow to go from left to right, it would take quite a bit of effort to go around this grain. But actually, if we were to go from top to bottom, you can see that that's actually fairly more direct. It doesn't have to do this twisty turn that it did from moving to left to right. So there are some examples of the differences between porosity and permeability. We have a few other words that we use to describe the groundwater system, and these are called aquifers and aquitards. So an aquifer is a sediment or rock with high permeability and porosity that has the ability to contain water. We refer to our groundwater systems as aquifers. You might have heard that used either throughout this class, or it's used pretty frequently in the news when we talk about agriculture and how the aquifer is dropping, or you might have to exploit a new aquifer or something. So you may have heard that word before. And an aquitard is a sediment or rock with low permeability, regardless of porosity, but typically also has low porosity that slows or impedes the motion of water. And this is, we usually see aquitards that bound the aquifer, and therefore we get a confined aquifer versus an unconfined. So an unconfined aquifer is one that reaches the Earth's surface, and a confined is one that's isolated by an aquitard. So here on the diagram on the right, this picture here, we can see that This layer would be an example of an unconfined aquifer because there's just sediment above it, and it can be recharged from rain. That's what this is supposed to show, that water can seep down through the surface into this unconfined aquifer. Now, below that is we have a layer here, an impermeable layer or an aquitard that protects the aquifer below it. And this would be a confined aquifer, that it's being bound, it's being protected from something above it. So when we talk about a low permeability and generally low porosity rock, what kind of rock would you think that would be? Where do we see these things in the subsurface that would represent like an aquitard, an impermeable layer? Typically, we see those in clays or in shales or things like that that have very low permeability, and they impede the flow of water. So when we talk about an aquifer, we also talk about the water table. And the water table is the horizon that separates the unsaturated zone from the saturated zone. So in an unconfined system, we have our surface here and our lovely trees. We have soil and usually unconfined sediment. And then below that is where we have saturation into an unconfined aquifer or bedrock. And that's where we get water that's filled the pore spaces. And so this is a diagram that represents the water table. And that zone between the unsaturated and the saturated zone is called the capillary fringe. And this is where some water seeps up from the water table due to surface tension, but a lot of it remains contained within the pore space of the rock below it. Okay, so we talk about the water table again, and we think about different systems where we have recharge into the water table. The diagram on the left shows that we have a lot of rain. This is a wet environment, and we have a fairly high water table that we see horizontally across a pond. So this would be an example where there's often rain that recharges it. It's very close to the surface. And this horizontal line represents where the water table occurs. And then on the right, in drier regions where you don't have a lot of rain or a lot of recharge, the water table is likely further below the surface. And that's what this represents, is that a lot of water lies a few feet, dozens, maybe sometimes hundreds of feet below the surface. And these arrows indicate where there's like flooding, or say there is recharge not consistently, and the water would want to flow into this topography low, this valley. Water would then seep into the subsurface and distribute itself towards the water table. That's what these arrows indicate. And so let's look a little bit more about the water table shape and things that can impact it. So I'm going to close my video here so you can see the whole diagram. So the water table can have shape. So in hilly regions, the water table is not just a surface, but can also mimic the overlying land surface. We think of it sometimes as being a horizontal line, but that's not always true. Here's an example of the water table, which is represented by this dashed blue line. And we can see that the water table changes based on topography. And we can see here that the water table intersects where there's a river or a pond. And we can also tell that from this, the flow of direction. Now, it's fairly intuitive that if it were to rain here, that water would flow down onto the slopes from a high topography level to a low topography level. That's not any different for water. We would expect that water would flow from H1 to H2. And that also has to do with the differences in pressure. There's more pressure at point 1 than there is at point 2 because there's a whole bunch of elevation difference here. And we have a lot of water at this location, putting pressure on this point, and less of it here because we're at a lower elevation. So we have high pressure at point 1, lower pressure at point 2, and we expect water to flow from H1 to H2. Now, in more complex systems beneath the surface, this is very ideal here in the top right corner. We see things like lens-shaped layers or perched water, and these are localized, isolated pockets of water. So when we have lenses of aquitards, we usually see water that sits on top of that, and this is called perched water table. And then typically below perched water tables, we do see either confined or unconfined aquifers and combinations thereof. And that's because these layers are not always continuous. So in this ideal example, they are continuous, but they often aren't. So the Earth is not perfect. It's not always predictable. So we always have small lenses of different sediment. And if we have small deposits of impermeable layers like clays and shales, we typically see water that sits right on top of that. Okay, so I jumped the gun a little bit on this, but I explained a little bit about how water would move in this example. And this is called, the difference in pressure here is called the hydraulic head. And that's the pressure within the water that provides the energy to cause groundwater movement, to cause groundwater to flow. So we have a change in hydraulic head from point 1 to point 2. And that's what I was saying before, is that we have a pressure difference. And again, we would expect water to flow from higher pressure to lower pressure. It wants to relieve that pressure. And so it goes from a high pressure situation to a low pressure situation. And we would expect water to flow from H1 to H2. Now, if we look over at this other hill, if I were to name this point H3, and this point up here, H4, which way do you think flow would move? Well, we've already established that water is going to go this way. And in this situation, we would expect between H4 and H3, we would expect the groundwater to move this direction because we have a greater pressure here and a less pressure here. Again, on this side, if this is H5, H5, we would expect water to flow from H4 to H5. Again, groundwater generally flows from regions of high hydraulic head to regions of low hydraulic head, from high pressure to low pressure. And groundwater flow paths can be calculated and modeled. And this is something that's done pretty frequently when we look at groundwater plumes, or if we look at discharge areas, if there's contamination and things. It's important to understand the direction of groundwater movement in order to try to remediate any of groundwater contamination flows. Again, if we have flow from high topography to low topography, we're going from a high hydraulic head to a low hydraulic head, and groundwater is going to want to move in these directions. It's also going to want to go towards recharge areas. So first, if this is dry above, the water is going to percolate down into the surface in order to intersect with the water table first. So this is our recharge zone. Water is going to go down first. It's going to try to meet its friends at the water table first before flowing into high pressure to low pressure areas. Of course, these examples that I've given you have been some idealized situations, but the subsurface is very complex. We've had lectures about subsurface structures and faults and things like that. So groundwater can take a long time to get from point A to point B, and it's not always the most direct flow. Sometimes faults can act as conduits, which means that flow can behave more quickly across a fault, or sometimes a fault may inhibit flow. So there's different situations of where that would occur and why that would occur, but understanding that the subsurface is very complex shows that groundwater flow is not always direct. It does take a very long time. So here at the diagram on the right, if we have recharge from a rain system up here, and we expect the water to flow from high pressure to low pressure, and say that we have a fault here, it'll take a long time for water in these different layers to reach a discharge point. So say that this discharge point is a water well, for example. Majority of the water that we're going to get could be from layers below, but if we see in this diagram, this simplified diagram, from recharge up here could take years, and in the lighter tan, this takes centuries and millennia down here. So if we expect a drop of rain from over here to be collected at our discharge point over here, that could take millennia to get there. And that makes it easier because we have this fault that acts as a conduit. And so groundwater can also flow along joints and basements and all these different boundaries as well. So groundwater flow is very complex. The flow can be calculated and described by an equation called Darcy's law. It's a function of hydraulic gradient, which is basically the slope, and the hydraulic conductivity, which is how easily flow can move. So hydraulic conductivity is a function of permeability and the fluid's viscosity, so how easily it can flow. And the hydraulic gradient here, we see that that's basically the slope between 0.1 and 0.2 here, and the distance between H1 and H2. So that's the hydraulic gradient. And we can measure this and we can understand groundwater flow using Darcy's law. Okay, so here it is. Don't be too afraid of this. It's a fairly simple equation. Again, Darcy's law describes the flow of fluid through a porous medium. It also gives a relationship between velocity, how quickly the flow can move, and the conductivity and the hydraulic gradient. So the hydraulic conductivity is represented by K. That's the measure of the soil's ability to transmit water. Again, the hydraulic gradient, H1 minus H2 over L, was that equation I just showed before. So Darcy's law represents the velocity, how easily fluid can flow. It's a simple calculation, and we use it fairly often to describe fluid flow and the velocity of that flow. So now let's talk about groundwater supplies. So when we talk about where does our groundwater come from, it can come from springs, for example. So if you've ever visited a natural spring, you would be drinking water that came right from the groundwater table, where the ground intersects the water table directly. This is where we have where flowing groundwater reaches a steep impermeable barrier, and then it pushes the groundwater up to the surface. And springs are natural outlets, and a lot of towns were established due to the presence of springs because they made it very easy to have drinking water, and that could be used for municipal or agriculture uses, as opposed to having a well that you have to drill or something like that. So springs are naturally occurring. And they occur where there's perched water intersects the surface of a hill, for example, or where there's downward percolating water that runs into an aquitard and migrates along the top surface of a hill slope. So here's an example of where we have perched water and it intersects the hillside here, and this is where we would have a natural spring. So the picture on the right is a natural spring wall seen on the wall of the Grand Canyon here. Springs can also occur where there's a network of interconnected fractures that intersect the water table and provide a conduit for groundwater to reach the surface. We can also see it where the ground surface intersects a natural fracture, like a joint, and taps a confined aquifer, and where there's pressure sufficient to drive the water to the surface. This is also known as an artesian spring. Artesian spring. Okay, so if you don't have a spring, how else can you get groundwater? Well, a lot of water today is from water wells, and water wells were discovered by digging holes into pits thousands of years ago. Today, they're built constructed with PVC or metal, They are usually cased. They sometimes require pumps. Sometimes there's enough natural pressure, but usually you have to pump the water. And there's a lot of design that goes into water wells. And how deep you have to drill a well is dependent on the depth of the aquifer. And so I'm going to put in the class notes a recommendation to listen to a podcast about groundwater well depths increasing over time in the like Fresno area based on agriculture. So there's a lot of agriculture in the valley, and groundwater wells have been produced deeper and deeper and deeper and deeper just because there's been so much withdrawal from the aquifer. So drawdown, so I just said a few of these words that are on this slide. Drawdown describes the amount of fluid that's removed from a water well. If the water is extracted further than it's replenished, a cone of depression can form. So if we have a water well that's, I like this comparison because we're like, oh, we have a little house here that just has a small well that's just probably being used for, you know, a family washing clothes, drinking water, and they have a small amount of drawdown versus a big well here. This well is serving some agriculture use here. You can see all these sprinklers. So this is going to have a significantly greater amount of drawdown. And the water that's being extracted in this situation is not being replenished as quickly as it is being withdrawn. And so what we see is a cone of depression where the water is being removed at a faster rate. Now, over time, what this diagram is showing is this is the horizontal line here represents the water table. And over time, as you produce this, as you can see, if we remove water, well, the water table is going to be overall lowered. And so if you continue to pump and withdraw fluid faster than it can be recharged, then you're going to continuously lower the water table. And what happens is agriculture can typically afford to drill a deeper water well and continue to use this resource. And then a lot of communities are then left with their own water well being dry because it no longer intersects the water table. So depletion of groundwater supplies is a huge problem. It's something that is regulated, and rightfully so, because some people are taking more than they should, and so it has to be regulated. So we see depletion of groundwater supplies very often. Here's an example in Florida, where there's a huge amount of urban growth, and through imagery we can see that it used to be green and lush, and now after some urbanization and irrigation and all sorts of things, that the river has been dried up, and because of all of the excess pumping to serve these communities, we can see that there's quite a bit of difference here with not as many swamps or not as much forest land and things like that. There's also a problem when we have a reversing flow of direction of groundwater, and that's where the cone of depression that develops locally changes the slope of the water table. The gradient may locally reverse, and reversals can allow for contamination or seeping from a septic tank, for example. So sometimes you have this cone of depression from withdrawal, and there's instances where you might have a reverse flow of direction of groundwater, and this is where we have an issue of contaminants that could impact our water supply. So you see this here, where if there is a contaminant that flows off of a septic tank, for example, it may not be as big a deal because the general groundwater flow is moving in a direction away from your water supply source. But then if you have continuous pumping from all these water supplies, it can change the regional flow direction and create these mini flow directions and create their own problems here. So this would be an issue if you have a water supply well so close to a possible contaminant. Another thing that we see is saline intrusion as a result of depletion of groundwater supplies. So in coastal areas where we have fresh water that is near the coast, we see that ocean water, salt water, can intrude into our aquifer. This was actually a really big issue in the city of Long Beach, where they withdrew so much water near the coastline that we would see saline intrusion, saltwater intrusion from the Pacific Ocean that would slowly invade into these municipal wells near the coastline. Another thing that we see is subsidence. We have pore collapse and land subsidence when you deplete the groundwater supplies. And so if you think about that drawing of these grains with water between them, that creates somewhat of a stable system. Now, if you remove that and then it's filled with air, those grains can further collapse or degrade. And what happens is the land cannot hold it up anymore, and it collapses, it crushes. And that pore space is then reduced. And we see land subsidence as a result of over withdrawal of fluids in the subsurface. So here's a diagram picture of that. So if we have a water table here that's normally filled with water, and we withdraw a bunch of water from it, and now these sediments near the surface are filled with air as opposed to water. We see small collapses here, and this is represented by cracks or fissures or scarps. And we see that overall the land is sinking. Here's an example of land subsidence. The picture here on this telephone pole represents how much the land has moved. So in areas of San Joaquin Valley in California, just over the Grapevine, land has subsided almost 9 meters between 1925 and 1975. And this has a lot to do with irrigation of farm fields. If you've ever driven through the Bakersfield area in San Joaquin Valley, you see a lot of oil and gas, and you see a lot of agriculture. And so this has a huge impact on land subsidence over the decades and how much water we withdraw from the system. So now that we've talked about withdrawing all of this water, let's talk about contamination. So human-caused groundwater contamination. So let's think about some contaminants that can enter the groundwater, some that may be intentional and some maybe not. What do you think? You've probably heard about some groundwater contaminants in the news, or you might see little alerts about contaminants and how you might have to boil your water or don't drink from certain sources for a little while. So some of the things that can cause groundwater contamination include agricultural waste, such as like fertilizers or pesticides or animal waste. We have things like industrial waste that can use organic and inorganic chemicals. And one that we see fairly often is a lot of contaminants as a result of landfills. The example I showed before was also septic tanks, and this is where we have a lot of bacteria and viruses that can enter the water. Petroleum products and chemicals that are not soluble, these things can enter our groundwater supplies if you live near the coast, or if you have stormwater. Sometimes they have little signs on the stormwater that says "Don't dump here" because it goes to a freshwater system, or it's not necessarily treated. So definitely don't pour your paint down the waste there. We also see radioactive waste. Those things can also contaminate groundwater. And we see acids that leach from sulfides in coals or metal mines. These are remnants left over from mining operations and things like that. All of these can cause groundwater contamination. So a contaminant plume is a cloud of these contaminants that move away from the source of the contaminant. We can model and estimate plume, we can estimate the flow direction, and we can do measurements to figure out where the flow came from or the extent of that plume cloud. So in this diagram on the right, we can see that we have a lot going on here. So we have things like fertilizer and septic tanks and surface tanks and all sorts of things that could be impacting the water table. So here is our horizontal water table, and these little red streaks here represent the contaminant plume. And so if these are entering our water table, we'd be able to look at the direction of flow based on other wells. Like we would be able to drill some of these wells and measure the parts per million contaminant of this specific soluble chemical or whatever it is. You'd be able to test the water for those things, and you'd be able to look at the different concentrations and figure out which way the flow is moving. Doing groundwater studies and modeling is something that I've personally done for a job. So one of the things that I looked at was using a program called ModFlow, which is free through the USGS, United States Geological Survey. And so if you're interested in groundwater modeling, if you're interested in this type of field, I highly recommend that you go online and look at ModFlow. And this is it's a simulation software that allows you to predict groundwater conditions, and you can input all of these things to look at surface water interactions, look at groundwater flow, contaminant plumes, all sorts of information that you could put into this model so that you can look at how groundwater moves beneath the surface. Okay, so in this lecture, we covered a lot. We talked about groundwater, where it comes from and how it flows. We talked about the nature of the water table and factors that determine its depth. We talked about wells and springs that can provide access to groundwater and how groundwater supplies can be damaged or depleted. So that's it for this lecture. See you next time.